Thank you, everyone. Very good morning. My name is Nasikul Islam, Nasik in short. So I'll probably try to go a little bit slowly, just to give you a little bit of what we do as in Exceed Geoenergy and what we're actually working on some of the projects. And a lot of our work is around supercritical CO2 and how we can manage generating heat and power using supercritical CO2 as a working fluid within the turbo machinery. So we are an operating developing company based out of Houston, Austin, Texas, and Houston. But we work across the US, and also we do have offices in Spain and in Mexico as well. Um, I think everybody has seen this, so I'm just going to frame this around the geothermal challenges in Taiwan. Um, just a little bit background. I am a drilling and completion engineer for 24 years, oil and gas. Moved into the geothermal side in the last year. But we're kind of really instrumental in transferring a lot of those knowledge and technologies that have been used in the oil and gas into the geothermal to accelerate development of the geothermal industry side of things. So a lot of challenges within the Taiwan geothermal market, as you see, but how we can actually rapidly get there. So there's a lot of focus on performance, a lot of training courses going on hard rock drilling, understanding the drill bits, and so really applying that is something I would probably put in context and in perspective. So excuse me. A lot of technologies that you see here probably are still being not being used in the geothermal industry. So if anybody knows what's managed pressure drilling or you know what are chimera type bits, which is a hybrid of PDC and the roller con, stuff around the chillers and the coolers, or subsurface directional drilling technologies. So all these directional technologies can be used to really drill under in the subsurface to reach the reservoirs where you wouldn't be able to reach from the surface. So this is a well-utilized technology in the oil and gas. If you look at offshore drilling, there's only few platforms, and you have 100 wells from that one platform that is being drilled. So, if you think Indonesia is doing it with Pertamina, or everybody, around Petronas has a lot of wells, and today there are a lot of systems out there that you can actually monitor. Just like in an airline, they have a collision avoidance system. Even within the subsurface drilling, there is a collision avoidance system as well. So, and those are in real time that actually looks at anti-collision monitoring and all that. So, if you want to understand a lot of the technical, let me know. I can talk about that, but I'm not going to go much into details. Um, what Exceed solutions are, we are really gearing towards the carbon negative neutrality. We're gearing towards a very small land footprint mass. So I am originally from Bangladesh, and I know how much land is of value because it's a very, there's million people within a very small density, right? The population density is very high. Also, water use, we have to look at how much water is being used in the system, how we can actually, use the water very conservatively, because there's a lot of water with arsenic, or how do we actually get all that, So those are very close to my heart. So I think that is one thing that we are really looking at doing, and that's why we use supercritical CO2. So some of you might be questioning why our preference is supercritical CO2 as a working fluid. A lot of the reasons behind, footprint, behind how much energy density we can generate using the supercritical CO2 turbines, and how much also water do we use. So we don't want to frag the wells because we know that that is a sensitive topic with water use, and how much that water cost is going up today as well. Um, a quick, I think demonstration. Yesterday, one of the speakers on the panel did talk about one of the closed loop systems they had earlier on. So we kind of modified that, but it's a different technology approach in modification, where we have really upsized a lot of the casing design, and where we're using the supercritical CO2 from a liquid, pumping it, into the injector well. Yeah, sorry, let me go back here. So this is a little bit better to show. Is we have an injector well with a different size casing, OD and ID. We are drilling deep, so a lot of these wells are in Texas, which go up to about 18,000 feet or 6 kilometers. And today, 6 kilometer wells are being drilled in 22, 25 days in Texas. Of course, it's different, but just to give you a little bit of the context in performance, I mean, formation-wise and everything, there will be, plus minus variation, but it still can be achieved, right? And I think if you're looking at those 6 kilometer well, we're basically drilling an injector well. We inject supercritical CO2 in a liquid phase using a thermosyphon effect. It will actually change into a supercritical CO2 around that temperature gradient. And this is my reservoir temperature at about 200, 220 degrees C, 12,000 PSI, whichever that is in bars. We do connect the wells, and so we do utilize a directional system to kick off and land and drill a almost just 400-meter lateral. It's not a huge lateral. It's about 1,200 feet or 400 meters. Again, because we're using supercritical CO2, we don't really need such a long lateral length. And then we are connecting the other producer well, but this producer well also acts as a secondary storage system for the CO2. So I can actually capture and have an energy storage system to connect to my producer. So we'll have the supercritical CO2 turbines on the wellheads and then with the generator skids. So this is a very small footprint compared to what any other traditional turbine system would look like, because we don't need that much of a big cooler systems or anything like that. So that's sort of the overall process for the supercritical CO2 system. I think I've talked about the closed loop. So yeah, advanced drilling. So the Exceed Geoenergy, before it became Exceed Geoenergy over the last 4 years, used to be an Exceed directional drilling company. So where with the high temperature, directional tools and motors, where, basically, so there's a lot of the experience that comes from the directional drilling, and then we kind of combined with the drilling and completion side of things. I used to work for an operator. So we actually were kind of combining a lot of the oil and gas with renewable systems. So our team is also made up of folks that come from wind and solar. So we've really created a diversified team that can actually scale up the system. Our current plans or projects on the roadmap are with a 10 megawatt PPA. There are 3 PPAs we already have for different utility companies. Basically, we should be spudding more. Stay tuned this year, but we'll have more technical presentations in the GRC coming up and some of the SPEs. So I also am a board member in the Geothermal Rising Conference and also the Society of Petroleum Engineers, where we have a lot of communication between the oil and gas and the geothermal community. So there's a big group. So in fact, I'll put my SPE hat now a bit and say if there is there's a geothermal technical section, GTTS, which has some representation in the Philippines, in Indonesia, but I don't think there is one in Taiwan. So I definitely like to touch base with someone of you to have that representation here. I am in the administrative board as well, so happy to connect with some of the folks there. But it's really great for technical exchange and ideas, and to really accelerate a lot of the talent and local talent force. So one of the other thing I talked about footprints. So normally, if you look at a steam turbine or a different type of turbine with a lot of coolers, you're really looking at, and there's literature published with a 20 megawatt turbine would be probably a 20 megawatt turbine would be twice as big as a 10 megawatt supercritical CO2, because these are radial type turbines. They can be stackable on top, and they can actually, they do have a radial inflow and axial outflow flow. So they're really kind of very efficient use of small turbines, because initially these were designed for the SMR industry, which we are kind of using with our supplier, that we can actually make them very modular and scalable. One of the things about megawatts, you can actually look at 0.6 hectares per megawatt, or the 2 acres 1.5 acres per megawatt, basically. Um, Yeah, so we do a lot of risk mitigations, and I think the previous presenter were talking about geomechanics, and yes, so we definitely look at a lot of the geothermal modeling, because all about the thermodynamics is how does my heat transfer across my reservoirs. So basically, you're going to be looking at a lot of that reservoir simulation to de-risk understanding in different hot rocks, in sedimentary basins, in different type of geologies, right? So we want to understand that delta T temperature. So I showed you my producer well. The temperature difference should not be huge, because if you lose a lot of temperature in that producer well, then you're not really transferring that into the enthalpy, which will create your work done to move the turbine, right? So your enthalpy and entropy needs to be definitely controlled. So that's why that temperature, the vertical wells is cemented, making, it's insulated. Somebody talked about insulated drill pipe yesterday, insulated casing, that can be done on casing as well, but you also have to have good cement to surface, not for just insulation, but also for well integrity purposes, so that that well can last for 30 years. So when I talk about well construction, it is actually another thing to notice is drilling plus completion plus production, the entire well life cycle. It's not just a drilling side of things. So that is something to also keep in mind, that when we de-risk the technology, it is for the entire well life cycle for 30 years. We have seen some of these strength, weaknesses, and opportunities, but I think as it consists of maybe Taiwan, is you're looking really what can be some of the threats within this type of technology. Or again, it is definitely it's a new one. Everybody will have different reservations about it, but obviously it is, again, who knew that the fracturing couldn't generate power in the old days, right? Or unconventional oil. So there was a lot of that technology has kind of moved forward. So we believe strongly that this is also going to take over at some point in different areas at different places, right? These are some of the wells we are planning already. There are 3 projects in plan to be spudded later this year. Spudded means starting to drill, basically. And a lot of our the wells are, as you can see, they are directional, but only about 1,200 feet here, or 400 meters laterals, and each wells would be 150 meter apart, or 150 feet apart, and that's based on that reservoir modeling to make sure we can drain as much heat as possible that we can actually produce from the producer well. This is not a mixer, by the way, that makes cake. So just to kind of, sorry if you missed the humor, but. Yeah, so as you can see, these are, so wellhead design is also very important for the well integrity. So I have to look at my casing corrosion, CRA, what kind of insulation I have inside here, that I can actually, because there will be some temperature loss through the connections, and so we want to minimize it as much as possible. So I do a full thermal heat flow modeling in the wellbore, in the reservoir, to really see what my temperature delta, to create that enthalpy to make the work, right? So a lot of these, these wells here are just surface-wise 50 feet. Now, they can be compressed even further. Oil and gas has actually drilled 10 feet apart, which is only 3-4 meters. I have myself drilled 7.5 feet on surface. So you can imagine, so again, think about an offshore limited place that you can actually put your wellhead, how many wells you have on surface. But because all the work is in subsurface, in directional drilling, that is easily possible. So your footprint on surface is very minimal. And we can also contain that wellhead underneath. So we can dig an 8-foot cellar, or about a 3-meter cellar, and we can encompass that to make it completely invisible from the surface, right? So it's neat and clean, and lot less distraction. So this is a little bit of the enthalpy. I can talk more details about the technical aspects of it, how we are really looking at. So each of these are the points. My one is the reservoir sink at a certain temperature and constant pressure. My 2 is the point at the producer, at the inlet of the producer. Then as I come up, I will have some loss of temperature that will create that work. And 3 to 4 is basically what's creating the work, within the turbine. So that modeling is critical. Supercritical CO2 has specific properties with very low specific heat capacity. That means it heats up faster. It has less frictional pressure. So if you don't really, you can drill with supercritical CO2 deep. Sorry, we're drilling with water-based mud, but we're evacuating, displacing that well with CO2 on the completion side of things. Okay, so it's not that we're drilling with CO2. So sorry. We are drilling with water-based mud, just the normal way to drill the well, and then we're displacing that with CO2. So CO2 is the carrier fluid that would actually transfer that fluid. So we have that CO2 will be flowed at a certain velocity, and then we do have to do some reservoir modeling to understand the thermal drawdown effect, because that is also important. We don't want to flow too much that it declines the production very rapidly, and a lot of that also. So if that pressure also reduces, then there are ways to kind of create a different convective system, pipe in pipe, or we can actually put an ESP at certain depth to keep that pressure in tune. So we still get that output that we want. And right now, a lot of the simulations are showing about 10 to 15 megawatts per well loop. So basically now you're really looking at a higher energy density being produced per that unit area and unit volume of CO2 captured. This is a quick, this is for a 150 megawatt project, just a sort of a, we do use some coolers, but we're not really cooling it too much because we don't want to cool that supercritical CO2 to way below the supercritical state, because then we have to heat it up again. We want to maximize the use of power. We don't want to have a lot of residual power. So the net effective power has to be high. That's why we don't want to use too much energy to cool or any other pumps to heat up the CO2. Yeah, this is available. This is published. This is in literature. There's a lot of reasons why CO2 is being used instead of water, and again for supercritical, supercritical nature of it. Just to kind of go back into drilling performance-wise. So drilling performance-wise, I was talking about 6 kilometers within 22 days. That's basically what you want to be targeting for a really low number of LCOE. How it can be done, definitely a lot of planning and a lot of lessons learned from one well to another, and basically how you can actually get those sections through. A lot of wells are actually drilled in a horseshoe well today as well in the oil and gas, but so I'm going to rush through some because I think my time is up, but a lot of these is what I was talking about before in terms of active drilling of tests to really understand the energy that you're going to be inputting to produce that ROP, right, or rate of penetration. A lot of our partners are well known. University of Texas is also working with them, and I think that's our team. Yeah, I think that's just my.
Yeah, thank you. Is there any question here? Yeah.
Yeah, I got one. Is it 6,000 meters surface to surface or the TVD?
TVD.
Thank you.
TVD is through vertical depth. Anybody that?
Yeah.
So I have two questions. One is how much amount of CO2 we are talking about here? And the second question is there any evaluation of well integrity under different level of seismicity to prevent leaking for your system?
So the first question is how much volume of CO2 based on the volume of the casing and ID of the casing. In our wells, we have about 10 to 15 metric tons per well. So that's 20,000 barrels in US units. Integrity-wise, obviously, this is why having a good cement to surface, making sure that that well All the wellheads, the casing is all CRA rated. You know, the corrosion resistance alloy. There's NACE 15, NACE 25, different materials. So yes, but without obviously breaking the bank, because I also have to optimize that my AFE doesn't go up my budget in terms of authorization for expenditure, and I also have to keep reality in check. So obviously those scenarios we have to do a lot of the probabilistic estimation. So I do a P10, P50, P90 in all my well planning to make sure that I'm actually within that P75 at least, and I can have the variances. So then, all the project planning, that's why that it's very important to plan the well. So planning takes 50% of my time, and maybe execution while drilling will probably be 30%. Right?
Thank you.
I know we know that the CO2 is very corrosive, right?
Yep.
So what your material to put into the casing?
So CO2 is corrosive at low pressure pressures. So you're really looking at low pressure pressures, and that CO2 that's why we are displacing it with pure CO2 that we don't have any water in there. If there is any kind of water, would have to have different material like Inconel or to overcome that. But all our designs are assuming maybe 1% water. So we actually do the due diligence of a flow loop test. And because we're talking about high flow rates as well, any kind of paths for leak resistance. But in those weakest paths, we usually upgrade that with different Inconel. So instead of using Inconel for the whole casing, I'll actually use it only on those leak paths.
And
that's how I
also
optimize
the
my cost.
thread of connection as well, because the tubing, the thread, because that's going to be special, because otherwise you're going to be easier to leak, not only the cement.
Correct.
Gas leak type probably not good enough. I don't think, probably you have.
Correct. So there's definitely some casings which are, looking at, especially like from NHK or Sumitomo. Yeah, we're looking at modifying a lot of those casing connections. But so they're definitely not API. There will be the premium metro-to-metro seals.
One more question. What's the in-house, like you mentioned on the last slide, that the in-house
Sorry, I can.
electricity in-house, how many percent? Because if you have a lot of the energy to compress, to critical and pump and then return again, so it's going to be like 20%, 30% of the gross profit. Because for example, like you need 10 megawatt, right?
Right.
So what's the install capacity, like 15 or 13 or so? What's going to be a lot of energy?
No, so our 10 to 15 megawatts is based on the mass flow rates. So we control the mass flow rates. So basically, we're just using m dot c delta t. So between the two, we want to make sure that's why we have a different casing IDOD to really produce that. And we don't want to have additional power sources like auxiliary power sources to eat up that power. We want to have as much 15 megawatt to be produced. So the residual is about only whatever we are probably taking is 2 to 3 megawatts less.
Like 30 to 30% of the cost.
Yeah.
Thank you.
You sort of told me that you also have pipe-in-pipe design for this kind of project. Can you show us that?
The pipe-in-pipe is a contingency if, only and only if. It's not something that we are, it's a back of our, so any planning, we always have to have contingencies. If we are not really getting that production decline, if we have production decline, we'll have to use a pipe-in-pipe.
Okay.
So
why you decline?
right. Yeah. It's like a secondary recovery technique would have to use.
Okay.
Yeah.
Okay, is there any question? And then we'll keep going. Okay. Thank you.
Thank you.
Really amazing talk and very fantastic new technology.